Welcome back. We have been looking at the real time task scheduling, and we said that we will start with the simplest schedulers, and then as we proceed we will look at more sophisticated task schedulers, and different operating systems depending on their sophistication they use different types of schedulers, and we said that the clock driven schedulers are the simplest scheduler. In the last lecture we started looking at the simple cyclic executives, and then we looked at the table driven scheduler, and then we had started looking at the cyclic scheduler. We had mentioned that in the table driven scheduler the operating system maintains a table of the tasks and their time of execution, and it sets a timer each time. The table driven scheduler is that requires setting up timers, one shot timers and number of times, and this is a major overhead because we are talking of simple operating system requiring only 1 millisecond or less for each scheduler execution, each instance of execution of scheduler at the scheduling points. And then we had said that the cyclic schedulers overcome this problem, and also these are much more sophisticated in the sense that they can handle multi-rate tasks, tasks requiring execution in different time periods, and that too efficiently. They require setting a cyclic periodic timer only once during the system initialization, but setting up the schedule for a cyclic scheduler is non-trivial compared to a table driven scheduler or a simple cyclic executive. And we had said that if there are n tasks with different periods, then the period for which the schedule needs to be developed is given by the LCM of their periods. During this LCM, some tasks may repeat multiple number of times and some tasks may just occur only once. So, this LCM of the period is called as the hyper period or the major cycle, and then the major cycle is divided into frames, equal sized frames, and the periodic timer is set to give an interrupt at these frame boundaries, and each time a periodic timer interrupt comes, the scheduler runs and decides the next task to execute by consulting the schedule table. Setting up the frame and assigning the tasks to the frames is a major challenge in this cyclic scheduling. Now, let us proceed looking at how are these frames decided, frame duration, and how are tasks assigned to the frames. In the major cycle, the tasks are assigned to frames. Let us say this green task to this first frame, a red one to the second, yellow one to the third, and so on. And in the next major cycle, they are repeated identically. So, basically the cyclic scheduler stores schedule for one major cycle which may have some number of frames, maybe let us say 12 frames, and then the schedule table will have entry 12 entries, and each entry will identify which task or which program to run. Tasks are basically programs in these simple schedulers. So, the first one program 1, program 2, next, etc., are to be run. So, the major cycle is decided by the LCM of the task periods, and even when the tasks have arbitrary phasings, still the cyclic scheduler can handle this, because for few initial cycles until the phase time, the frame assigned to the task will remain unutilized, because the task instances will start arising after the phase is over. But what if the frame size does not divide the major cycle? We said that the LCM contains an integral number of frames, or in other words, the frame divides the major cycle. If it does not, the frame does not divide the major cycle, then we have some frame which does not complete at the major cycle boundary, and therefore, the schedule has to be stored much larger than the major cycle, and that is the reason why one of the requirement for setting up the frame size is that the frame size must divide the major cycle. Otherwise, the schedule length to be stored in the table will be much larger. So, we can assume that in a typical application, we will have the minor cycles or frames squarely dividing the major cycle, and the frame boundaries are marked by the interrupts generated by the periodic timer. So, this is the major cycle, which is decided based on the task periods, is the LCM of the task periods, and then that is divided into an number of frames. All frames are equal size, and then as the periodic scheduler is set to give a interrupt after every frame length, as soon as the interrupt from the periodic timer comes, the cyclic scheduler starts running, consults the schedule table and executes the corresponding task that is mentioned in the table, and the task may complete early, that remains idle, and then the next frame boundary occurs given by a interrupt from the periodic timer. The cyclic scheduler becomes active, consults the schedule table, finds the task to run next, which is P4 in this case, and then initiates execution. It completes early, and then the next frame, and so on. And after the major cycle, this schedule is repeated. And see here, the small length of the red line shows the execution time, indicative execution of the scheduler execution, takes very small time compared to the task execution times. So, these are efficient scheduler. In each schedule, the work required is small. As soon as the interrupt occurs, just consults the schedule table and start the execution of the corresponding task. There is no other activity, no timer setting, nothing, because it is a periodic timer. It is set once during the system initialization time. So, a typical schedule table would look like the different frames and the tasks that are to be executed. Of course, we have shown this for our understanding, but then in a real task table we need not write the frame number, etc. So, we just store the sequence in which the task to be executed. So, just name of the programs executables that to be executed, and the scheduler just indexes in this array of the vector of tasks, and then finds out the current one, initiates execution and increments the entry to the table. We have already mentioned that one complication in using a cyclic scheduler is constructing a schedule. Two important aspects here. One is how to fix the frame duration. The second is about assigning tasks to the frames. So, after doing both of these actions, we will have the schedule table where we have the frames and the tasks. So, let us look at the nitty gritty of how to develop the schedule table. So, the steps that we need to do to develop the schedule, the first thing to do is to choose the frame size, and then we may not be always successful in the first attempt to get acceptable frame size. If we get acceptable frame size, then the job is rather easy. The next step would be to place the jobs into the frames, but often we will see that no frame size is suitable. In that case, we need to break some of the jobs into smaller jobs, because as we will see through the examples and the methodology is that the jobs which take large execution time, they are the culprits which hinder finding a proper frame size. These make it difficult for setting the schedule, and we may not be able to find the correct frame size. And remember that these are simple scheduler, these are not preemptive, only the start execution of a program in each frame, and it is not that some high priority task can arise and then we have to preempt some tasks, etc. Nothing. Here we have a simple table here, and the interrupts corresponding to the frame boundaries, and the cyclic executive simply consults the schedule table and just starts execution of the corresponding task. Let us look at one example here. This we can do even without much background. So, we have given this simple example here. So, we have 4 tasks A, B, C, D, and each job, the task instance is defined by the computation time required. So, A requires 1 millisecond, B requires 3 millisecond, C requires 2 and D requires 8 millisecond. The period is 10 for the first 2, 20 for the next 2, and the deadline is same as the period. So, before the next instance, next job arrives for this task, the task must execute. So, D is a large task and we divide into 2 and 6. Right now, it may not be clear why 2 and 6, we will see that. So, here the major cycle is 20, which is LCM of the period of these 4 jobs, which is 20 millisecond, and let us say we want to select a frame size. Each frame size must squarely divide the major cycle, and therefore, we decide to choose 10. But then why not 2, why not 5? As we proceed, we will see that each frame must be able to accommodate at least any job. So, any job should be able to run to completion in one of the frames. So, the possible frame sizes are 1, 2, 5, 10 and 20, and 1 to 5 cannot be used because we have a job here requiring 8. So, you can choose 10. So, then once having chosen that, we can place these in the different frames, but let us look at more insights into how to do that. So, in this case the cyclic scheduler is simple. If it is frame number 0, there are 2 frames. If we select 10, it runs A, B, C, D, otherwise it runs A, B, D, and then the frame number is incremented. Now, let us see what are the constraints in choosing the frame size. The first thing is that the frame size must be larger than any task execution time, because each task must be assigned to one frame and it must complete its execution in the frame. So, that is sets the lower bound on what can be the frame size. So, the maximum execution time of a task, that is the lower bound for the frame. We cannot make the frame any smaller than that. The second constraint on the frame size is that the frame size must divide the major cycle or the hyper period. And the third constraint that we would need is that between the release time of a task and the deadline of the task, there must be at least one frame. So, the time at which the task recurs, so this is the release time and the deadline, there must exist at least one frame. To think of it, why this is necessary is that if the task arrives, the task instance or the job arrives or is released after the frame boundary, then we cannot assign that to that frame, because at the frame boundary the scheduler must initiate the execution of the job. So, if the job arrives after the frame boundary, we cannot execute the initiation of the job in this frame, and the deadline, if it is somewhere here or within this frame, then of course, that job cannot complete execution before the deadline. And that is the reason why we need at least one clear frame to exist between the release of a task, of any task, before it, at the time it is released and the time of completion, the deadline, there must exist a clear frame. To explain this further, just want to take some examples and with some diagrams I will explain that further, that why we need one frame, one clear frame to exist between the release time and the completion time. But before that, the first thing is that the frame size is an important design parameter, and there are 3 constraints that the frame size must satisfy. One is that it must squarely divide the major cycle. The second is that the frame size must be larger than the largest job size. The third is that between the release of every task and its corresponding deadline, there must exist one frame. The first two are easy to check, that whether the frame size divides the major cycle squarely or not. The second one is also easy, that the frame size must be larger than the largest task size, but it is the third constraint which requires us to do some thinking. That is, there must be a clear frame between the release of a job and its completion. So, f should be larger than the task size, otherwise it becomes complicated to run it, because each time the scheduler wakes up on a periodic timer interrupt, it must start execution of some job. And f squarely divides the major cycle, otherwise the schedule table will become large. So, now let us look at the third constraint. Between the arrival of a task and its deadline, at least one full frame must exist. So, this sets an upper bound on the frame size. As we try to select a frame size, we might find that multiple frame sizes are acceptable. Then we choose the largest frame size, because that minimizes the overhead, because the number of interrupts from the periodic timer become less number of time the scheduler runs. So, it is advantageous for us to select the largest frame size when multiple frame sizes are acceptable, which meet the constraints. So, this point we had already said that unless the major cycle is squarely divided by the minor cycle or the frame, then the schedule table length would become unnecessarily large. So, in every design that we undertake, we ensure that the frame size squarely divides the major cycle, or major cycle is an integral multiple of the frame size. Now, let us see why there must be at least one full frame between the arrival of a task instance, that is a job, and its deadline. Let us take this instance. Let us say we have this task instance I arrives here just after the frame starts. Obviously, this frame cannot start execution of this task, because the scheduler actives only at the start of the frame, and if anything whose execution is to be started, must be undertaken at this point. So, the execution of the T I cannot be started in this frame. The scheduler can only take up its execution in the next frame, but then by that time its deadline is very near. So, the task time may extend beyond the deadline. So, there is a chance that the deadline will get missed, and that is the reason why in our design we will insist that the frame size must be set such that there is a clear frame between the release of a task and its deadline, and that sets the largest size of the frame. So, now our design problem is that how to decide which is the minimum size of the frame. which is the maximum size of the frame that we must choose based on this constraint, that there must be a clear frame which must exist between the release of a task instance and its deadline. Obviously, if our frame size is larger than the task instance and its deadline, we may not have a clear frame which exists between these, but then can we do better than that? We will come up with this simple expression that GCD f comma pi. We will not go into the details of the derivation of this expression. GCD f comma pi is gives the size of the frame. So, 2 f minus GCD f comma pi less than di must be satisfied. So, the worst case occurs for any task given by the GCD f comma pi. So, it may at most occur after GCD f comma pi of a frame. This is the worst case, and in this case, for the task to meet its deadline, we must have its deadline before the end of the second frame, because we may at most start its execution here. So, this much time has elapsed and this is given by f minus GCD f pi, and we have just one more frame is remaining. So, 2 f minus GCD f comma pi is less than di must be satisfied for every task, because GCD f comma pi indicates the worst case scenario where a task occurs just after the frame has passed, and therefore, the remaining time here for which the task cannot be started execution given by f minus GCD comma pi, and then the task may be taken up here and you have just one f left. So, the deadline, if it is here at the end, then we may just able to meet it, and that is what is expressed here. 2 f minus GCD f comma pi is less than equal to di, that must be satisfied for every task. So, these are the three constraints. The frame size must be more than every task execution time, 2 f minus GCD pi comma f must be less than di for every task, and the LCM of all periods, which is the major cycle, must squarely divide the must be squarely divided by the frame size that we write in this expression. F into LCM pi divided by f must be equal to LCM pi. So, this indicates that the frame size squarely divides the major cycle. So, these are the three constraints we must ensure when we want to select the frame size. We will find that several frame sizes are becomes possible. So, this we call as plausible frame sizes, and then even if we have a plausible frame size, it is not the case that schedule may be found, maybe because we have the total number of job instances to be handled is more than the number of frames in a major cycle. So, we have to be careful here. All plausible frame sizes may not be acceptable, we will see through some examples, and then we find the frame sizes which can be used, and then we choose the largest of those, because that will minimize the overhead due to the scheduler. So, we will stop here. We will start with few examples of designing the frame size and assignment of tasks to the frames in the next lecture. Now, we will stop. Thank you.